So, welcome. Modeling with transducers. You may recall that not even last week, 2 weeks ago on Friday, I know, it's almost unfair to assume that you remember any aspect of that, but we did a lecture, and it was on transducers, and we talked about how you can use a transducer to convert energy from one domain to another domain, or to change its form within a domain. So the two examples we used were the DC motor and the gears, right? So the DC motor converted electrical energy to mechanical energy, rotational mechanical energy, and the gears changed the form of the energy in a rotational mechanical system within a single domain. So we're now going to do a short lecture on how to model with transducers. And we started to look into them a little bit already. We talked about how there are two different primary types, right, of ideal transducers. One being a transformer, in which the across variables from one side to the other side are directly related, and the through variables are also directly related. And the gyrator, for which the across variable on one side is directly related to the through variable on the other side, and vice versa. So those were the considerations that we explored. And we now develop both linear graph and state space models of systems that include transducers. Our two main types of modeling are linear graph models and then state space models so far. We'll learn some more actually before the end of the semester, of course, which, contrary to popular belief, is 3 weeks plus finals away. I know. Okay, so linear graphs of two-port ideal transducer elements are drawn as shown in this figure. So the transformer is drawn like this. So you have two branches that are kind of coming together, coming near each other, and if we draw a dashed rectangle, it doesn't have to have the nice rounded corners on the rectangle. It really can be any rectangle. Then we are denoting that it is a transformer. Okay, so it's a two-port element, so it's got to have two different branches representing it. Similarly, the gyrator looks the same, except we cross over in the center to denote that it's a gyrator. Gyrator, it kind of makes sense because you cross between the two variables, variable types in the relationship. So once again, we use the sign convention that power into an element is positive. That also goes for this multi-port element. Often the branches are drawn toward ground nodes. So often these nodes are ground, unless your system wants you to do something else. There are some cases where it's not that way, so I didn't draw them always to ground in the diagram, but it is common to have that be the case. So often the branches are drawn towards ground, which are always different when the transducer acts between different energy domains. So for instance, if this was a motor, then this side would be voltage across variable, so this would be the reference voltage, right? And on this side, the ground would be the angular velocity, This is the motor. And it could be anything, but in this case, let's talk about it as if it was a motor. On one side, the ground would represent 0 voltage. On the other side, it would represent 0 angular velocity, or the reference of each. Yeah, so sometimes, however, so in the case of the gears, we had within one energy domain we were transforming, so the reference would be the same. So we could draw, the book actually draws it like this if they're from the same energy domain and just a single ground, so that the branches come together. Either one. You could even draw 2 and just say they're the same. I'm fine with that. It's up to you. Transducers may or may not be sufficiently modeled by ideal transducers. Okay, so these are ideal transducers that we've considered thus far. For instance, we may need to consider the moment of inertia associated with a gear. Okay? When this is the case, additional elements can be connected in parallel and or in series with the 2-port element nodes. So DC motors, another example, are typically not modeled with an ideal transducer alone because the windings have both resistance and inductance. So we'll add that to the motor model that we'll consider soon. And so let's say I like the let's get my eraser out here. It's not working. Anyways, delete this. So let's say that this was a gear situation, and maybe the sides 1 and sides 2 of the gear have a significant amount of inertia associated with them for the system. Maybe the gears are just large compared to the inertia load that the system is seeing. So we have to take into account the gears, the inertia of the gears. Or maybe they're connected, maybe this node is rigidly connected to some massive element. So we would then put in a J1, for instance. We might call it J1. And a J2 on here. And these would be shared. A shared ground. Because they're both angular velocity reference. So that's an example. Or maybe, in addition to that, one of them is connected to a bearing, and it has some bearing damping. So maybe we need to put in like a B1, bearing damping as well. And so that's fine. So we can use the ideal transducer as an aspect of a model of a non-ideal transducer. Okay? So that's important to know. It's not like we're stuck. Like we're only able to deal with ideal ones, and we know that none of them are actually ideal. So we're actually able to deal with them very naturally, even using these ideal transducer models by just adding in extra elements as needed. Okay. Good. So state space modeling, so that was linear graph modeling mostly. So state space modeling with transducers. We present a method for constructing a state space model of systems containing transducer elements. Just as before, we had a method of taking linear graph models and making state space models from them. We want to have that same method to include now transducer elements. This procedure begins, as before, with the construction of the normal tree. The following rules must be respected. There are 4 rules now. The first 2 are the same as the 2 rules that we had previously. So R1, the first rule, is there can be no loops, same as before. R2, every node must be connected. So normal tree is exactly the same so far. And then we have two more rules now, 3 and 4, that specifically talk about the transformer or the gyrator. So for rule 3, of a transformer's 2 branches, exactly one is included. So you have to either include one or the other. Disallowed is including neither or both. So you have to choose exactly one. Okay. A gyrator's 2 branches, you have to choose either both or neither for your normal tree. So for a gyrator, you have 2 options: either include neither of the branches or include both of the branches. So those are our rules, and the normal tree steps are exactly the same with one additional step. Okay, so step 1, include all nodes. Check, same as before. Include all cross-variable sources, same as before. 3, include as many as possible A-type elements, same as before. Now we're going to interpolate 4 in here. So include transducer branches, so transformer and gyrator branches, minimizing the number of t-types in the tree. So we have to respect these rules, rules 3 and rules 4, as always, rules 1 and 2, when we select these transducer branches. But respecting all those rules, we want to minimize the number of t-types in the tree. We haven't selected the number of t-types yet, so actually that doesn't happen until 6, right? So what we have to do is try one, see how many t-types end up. So try selecting, if it's a transformer, selecting the left one, for instance. Finish the rest of these steps, see how many t-types you ended up with. Then go back and select the right one instead, see how many t-types you end up with. You need to go with the situation that gave you the least number of t-types in the normal tree. So if you have a single transducer in your system, this is easy, right? There's just 2 possibilities at most, because maybe you have to select one based on these other rules. Maybe you'll create a loop or something. So at most you have 2 possibilities if you have one transducer. But when you start having more and more transducers, if you have like 7 transducers in your system, then there are 2 to the 7 possibilities, right? So it gets big pretty fast. It's important to keep in mind. I mean, there's no avoiding it. It's just how it is. It's sort of like the diodes. Remember when we did diode circuit analysis, we assumed that it was a wire and did an analysis, and we assumed it was open and did another analysis. Remember? And when we were like, okay, we got to choose. If it's one diode, it's not a big deal. There's 2 possibilities. If there are 10 diodes, 2 to the 10 possibilities. That's a lot. So it works better for smaller systems, but there's no avoiding it. So minimizing the number of t-types in the tree, we include the transducer branches, and then steps 5 and 6 are the same as before, d-types and t-types. And as always, if we reach a point where we can't select any more branches without creating a loop, we're done. The normal tree is finished. So state and output equations can be derived as before. So we have the normal tree. Now we can go through our steps, right? Our state not just state variables, but maybe our primary and secondary variables, system order, state variables, input vector, output vector, elemental equations, continuity equations, compatibility equations. We can go through all of that same stuff with one caveat. Each 2-port element requires 2 elemental equations. Everything else is the same. So once we have the normal tree, we're off to the races. Whenever you see a 2-port element, though, so if it's a motor or if they're gears or whatever, the elemental equation has there are two elemental equations for that element because it's a two-port element. So that's really the only caveat. Yeah. So are there any questions about that? Yeah.
I like the across and through variables for the transducer. Are they going to be in the primary and secondary variables?
That's a good question. They will be. Let's see. Hadn't considered this question before. So you still follow the same definition for primary and for primary and secondary. So primary variables are cross variables on elements in the normal tree and through variables on links. And secondary variables are the opposite. So it's still true. So your normal tree will be including and excluding branches from these two-port elements, these transducer elements. So it depends on, so which one's primary, which one's secondary, depends on if it's in the normal tree or not. Yeah. Cool. And a note on primary and secondary variables. The way that I have us set up the process, we can almost disregard primary and secondary variables. And that's only because of how we construct our continuity and compatibility equations. The way that I have us construct them is having us solve for the secondary variable in every case. But if you didn't construct them in the way that I did, you would have to know which variable to solve for, which would be the secondary variable. That won't get you into any trouble in the way that I do it. However, one of the tools that I gave you guys to solve larger systems is that website that Cameron Devine made. And so if you use the state Mathematica package, it doesn't matter. But if you use his website, you enter in the continuity and compatibility equations. You have to solve all of the continuity and compatibility equations for the for the secondary variable, and then the elemental equations all need to be solved for the primary variable. Otherwise, as I discovered the other night, it sits there and chugs, and I didn't know what was going on, and I was like, wait a minute, and I switched it, and then it worked. So then I realized that it was set up that way, which is fine. It just requires that you're aware of that fact when you enter in stuff. So knowing which ones are your primary and secondary are important if you're going to use that site. The way we set up the procedure, it ends up being irrelevant just by construction because we're clever about it. Because I don't like having to remember which ones are primary and secondary. I like to skip steps. I don't know if you've noticed that, but I like to do that. I like to get us, what's the path of least resistance, right? I like to go that path. So, all right. So that's all we have for this. So we actually are ready to